Back when the Electronic Industries Association was founded, having even one electronic gadget at home caused a great deal of excitement.
Traffic accident northbound Long Beach Freeway.
Now, over 60 years later, electronic products have become a necessity rather than a luxury. And as our use of electronics has grown, so has the Electronic Industries Association. Today, the EIA has become a full-service national trade association, representing the manufacturers of the ever-growing number of superb audio and video products that we all use and enjoy. Strategically located in the nation's capital, the EIA is responsible for communicating industry positions and developments to government agencies, the engineering establishment, consumer groups, the mass media, and the educational community. The EIA's Consumer Electronics Group sponsors hands-on seminars for technicians and educators, publishes technical manuals and textbooks, and produces training videos such as this.
The heartbeat of today's consumer products is the microprocessor. From the VCR to the fax machine, from the compact disc player to the desktop computer, consumer products rely on the microprocessor for direction and control. When the microprocessor fails, the product stops. This video will acquaint you with the basic components of a microprocessor, show you its use in typical consumer products, and discuss effective troubleshooting techniques. The microprocessor is a digital device made up of AND gates, OR gates, inverters, flip-flops, registers, and many other familiar digital components. Like its components, the microprocessor accepts and produces signals that are logic high and logic low. It typically is TTL compatible, which means that its primary power supply is a well-regulated positive 5 volts and that it expects logic lows to be less than 1 volt and logic highs to be more than 2 volts.
Microprocessors are at the heart of modern consumer products. Let's take a look at the components that make up a microprocessor system. Microprocessor system includes the microprocessor itself and several other necessary components, all of which are seen in consumer products. While a microprocessor is a digital device, it is very different from simpler devices like the AND gate. The AND gate will always behave in the same predictable manner as described in its truth table.
The microprocessor, on the other hand, is capable of dozens of different operations, including those of the AND, the OR, the inverter, and most other digital devices. Because it can perform so many operations, the microprocessor doesn't know what to do when it's first powered up. It must be told which operations to perform and in what order to perform them. Basically, all a microprocessor can do is execute instructions. When it finishes one instruction, it automatically looks for another. In fact, from the time it's powered up until the time it's powered down, a microprocessor executes instructions. The list of instructions used by the microprocessor is called a program. This, then, is the biggest difference between a microprocessor and simpler digital circuits. The microprocessor is very flexible, but it must be programmed. Without a program, the microprocessor is useless. Another component must be connected to the microprocessor to supply it with instructions. This component is the ROM, or read-only memory. ROM is a memory IC which stores the program and supplies the instructions to the microprocessor as they are needed. The program is permanently stored in ROM and cannot be changed or forgotten. For this reason, every microprocessor system must contain ROM. Each time the system is powered up, the microprocessor must receive instructions from the ROM. Some products employ a changeable form of ROM, known as EEPROM, double EEPROM, or E-squared ROM to store such semi-permanent information as favorite channel. While EEPROM's contents can be changed, they are not lost when it is powered down. ROM is an essential element of every microprocessor system, but another kind of memory is also needed. This is RAM, or random access memory. RAM is IC memory, which stores information that changes as the product is used. Such information might include the time of day, the mode of operation, digital audio signals, the cooking time and temperature, a document, or a consumer's program. This information cannot be stored in ROM since it is constantly changing. The amount of variable information needed during the normal operation of a product dictates the amount of RAM used in a system. Desktop computers require a large amount of RAM, while a compact disc player, or VCR, will require relatively little RAM. Finally, every microprocessor system needs to communicate with the other sections of the product. It must be able to read a keyboard, light a display, control the servos, or perform any other task assigned to it. The microprocessor cannot talk directly to these devices because of timing requirements within the microprocessor itself. A device called a port is used to interface or connect these external components to the microprocessor. While there are two kinds of ports, one for input devices and one for output devices, both are generally referred to as a port, an I/O port, or an input or output. Input ports allow the microprocessor to read keyboards and sensors and to receive information from other devices in the system. Output ports allow the microprocessor to send information to the front panel display, motors, servo controllers, and other output devices. A couple of other signals are essential for the operation of a microprocessor. One is the clock signal. The clock signal is the heartbeat of the microprocessor itself. It's a crystal-generated pulse train which is constantly supplied to the microprocessor and keeps the microprocessor executing instructions. If the clock signal fails, the microprocessor either stops or acts unpredictably. The last signal that's absolutely necessary for normal operation of the microprocessor is the reset signal. This signal simply ensures that when power is applied, the microprocessor will begin executing the program with the first instruction stored in ROM. If the microprocessor does not receive the reset signal on power up, it will begin executing instructions out of sequence. When this happens, the microprocessor and the entire product often operates intermittently, incorrectly, or exhibits a dead set symptom. All microprocessors must be reset during the power-up sequence.
This diagram, then, contains all of the major components in every microprocessor-based system. In addition to the microprocessor itself, we find the read-only memory for program storage, the random access memory for temporary data storage, input ports, and output ports for connections to the outside world. The reset and clock signals make sure that the microprocessor executes the instructions properly each time the product is used. Now, let's watch as the microprocessor performs the simple function of reading the front panel of a VCR and placing the unit in the play mode.
When the VCR is plugged in, the clock signal is immediately applied to the microprocessor, and at the same time, a reset pulse forces it to the first instruction stored in the ROM. The microprocessor interprets this instruction as a scan the keyboard sequence. It then reads the keyboard through an input port and stores the key code in the RAM. The next instruction is fetched from ROM and is used to interpret the key code as the play key. The next instruction fetched by the microprocessor is interpreted as an output function. The microprocessor then issues the play signals through output ports, which place the VCR in the play mode and lights the front panel display to indicate the action taken. This fetch an instruction, execute it, then fetch another sequence of events continues as the microprocessor monitors and controls the VCR.
Well, there we have the operation of a microprocessor system. What we've just seen applies to any microprocessor in any application just as it does to the VCR in our example. But there's one more aspect of a microprocessor system that we should discuss. The microprocessor systems generally found in consumer products are often called microcontrollers, microcomputers, embedded controllers, or system controllers. An embedded controller has all of the major microprocessor system components on a single IC. This is possible because the program to control a VCR or CD player is relatively small and requires little ROM and RAM. But because all of the microprocessor's system components can be placed on a single chip, the cost of the product is much less than if individual chips were used. Now, this doesn't mean that we'll never see a RAM or a ROM or an I/O interface chip in a consumer product. We obviously do. But the single chip labeled microprocessor always includes most of the system. Desktop computers, on the other hand, always use separate chips for each of the major components. You'll find that the RAM, ROM, and I/O port chips are separate from the microprocessor. Because the primary role of the desktop computer is to manipulate large amounts of data, this requires very large programs, large amounts of memory, and several serial and parallel I/O ports. We'll be looking at microcontrollers used in two typical applications, the VCR and the compact disc player.
This CD player produces great sound, but it could not do so without the supervision of the microprocessor. Let's take a closer look at the microprocessor that's used here, its signals, and some troubleshooting tips. The microprocessor here is IC101. IC101 contains the entire microprocessor system, including the microprocessor, the ROM, the RAM, and all input and output lines. This means that almost all of the connections to IC101 are input or output signals. The only exceptions are the external power, the clock, and the reset signals. The main power supply for this microprocessor is the 5-volt VDD seen here. The 5-volt supply is also commonly labeled VCC. The microprocessor IC101 is also supplied with a positive 30-volt supply to drive the front panel display. The first step in troubleshooting any microprocessor circuit is to verify the power supply levels. Without proper power supply voltage levels, the microprocessor operates either erratically or not at all. The DC supply should be measured with both a meter and with an oscilloscope. The meter should read within about 5% of the values shown on the schematic. Because the microprocessor is very sensitive to relatively low levels of power supply ripple, it's important to also measure the DC supply with an oscilloscope. The microprocessors used in consumer products can be tested with a dual trace 50 megahertz scope, but a 100 megahertz scope is recommended. So if you're currently repairing CDs or VCRs, the oscilloscope you are presently using will be adequate for the job. Microprocessors are sensitive to ripple levels that will probably not be apparent on the meter. A ripple of about half a volt on the VDD supply can cause erratic operation of the microprocessor. Only after the power supply levels have been checked and any problems repaired should further testing of the microprocessor continue. 2 additional power supply tests must be conducted before the power supply can be ruled out as a source of the problem. First, the ground connections on the chip should be observed using the oscilloscope. It might seem strange to observe ground, but a poor solder connection or broken run or foil on the circuit board can disrupt normal current flow, and the ground line can begin to pulse. A pulsing ground might be tolerated in an analog circuit, but it will cause unpredictable operations in a microprocessor circuit. Finally, many products do not use all of the signal lines available on the microprocessor chip. These unused lines are generally input and output lines that are either specifically designed for features not supported by the product or are input and output lines that are just not used. Some of these lines are left unconnected while others are tied to either ground or VDD, oftentimes through a resistor. The voltage level on each of these unused but powered lines should be measured. Unused input and output lines, which are the wrong logic level, can cause erratic microprocessor operation. A logic probe provides a quick and effective way to monitor these unused lines as well as other input and output lines. The probe should be set for TTL voltage levels and pulse mode operation. Its power leads should be connected to VDD and ground test points. The tip of the probe is simply touched to the pin being tested. The probe will indicate either a high if the line is connected to VDD or a low if the line is connected to ground. No indication of pulsing should be observed.
The power supply voltages must be correct for the microprocessor to work properly, so the power supply test should always be the first performed, and any power supply problems must be repaired before troubleshooting can continue. When servicing microprocessor circuits, remember that most components are susceptible to damage from electrostatic discharge. Notice that we're using a grounding wrist strap and a bench with a conductive work surface. We recommend that you use these procedures as outlined in the accompanying reference booklet.
The microprocessor clock signal is always generated by a crystal oscillator. The oscillator circuitry is built on the microprocessor chip, so only an external crystal is needed to generate the clock signal. A wide range of crystal frequencies may be found in the various consumer products. A 4 megahertz crystal is used here to generate the clock signal for the microprocessor. The rest of the clock oscillator circuit is built into IC 101. Notice the clock lines are labeled oscillator instead of clock. This is a fairly common practice that allows the clock label to be used for the signal used to coordinate communications between the microprocessor and other system components. One side of the microprocessor clock can generally be observed on the oscilloscope. Occasionally, the oscilloscope will load the crystal and swamp out the oscillator.
The clock is the second essential signal in every microprocessor system. After the power supply test, check for the presence of the clock signal. Be aware that some microprocessors will continue to operate if the oscillator circuit or the crystal is damaged. These chips can generate an erratic clock signal using the capacitance of the crystal leads or the circuit board foils. When this false clock condition occurs, the microprocessor may operate normally for a while, then begin to control the system at a faster or a slower rate than normal. Or it may work for a while, then stop, then start again. You can suspect this condition if the clock appears to be irregular when observed on the scope. Don't look for other sources of trouble in the microprocessor until the clock signal is present and normal.
The third essential signal in every microprocessor system is the reset signal. In this CD player, a capacitor connected to ground is used to automatically provide the reset signal each time the unit is plugged in and the microprocessor is powered up. This microprocessor employs an active low reset signal. Active low means that the microprocessor is reset when its reset line is held briefly at a logic low level, then pulled to a logic high level. The normal operating condition of an active low reset line is logic high. Other microprocessors utilize an active high reset. These devices are reset when a brief high pulse is applied to the reset input. The normal operating condition of an active high reset is a logic low. The first test of the reset input is to determine if it is in the proper state for normal operation. This can easily be done by monitoring the reset line with the logic probe or oscilloscope. During normal operation, the reset line should be in its inactive state. After its initial power-up change, the reset line should not be pulsing or changing. A pulsing reset line will cause erratic operation. Anytime the reset line is stuck in its active state, the microprocessor will be locked up in an inactive condition and the product will exhibit a dead unit symptom. Stuck reset lines are often produced by shorted support components. A test of the associated resistors, capacitors, and transistors often pinpoints the problem. If the associated components are good, lift the reset lead on the microprocessor. If the reset line is still stuck in the active condition, replace the microprocessor. To test the reset action of the line, an oscilloscope is connected to the reset input and the product is unplugged or turned off to remove power from the microprocessor. When power is applied to the product by either plugging it in or turning it on, the reset pulse should be seen on the oscilloscope. Sometimes it can be difficult to clearly identify the reset pulse. In these situations, some manufacturers recommend forcing the reset line to be active by momentarily connecting a low-value resistor, about 100 ohms, between the reset line and the active side of the power supply. This should cause the microprocessor to initialize or reset the unit as it does when power is first applied to it.
Remember that just because a reset pulse is applied to a microprocessor, it does not always follow that the reset operation actually occurs within the microprocessor. The microprocessor may be defective and unresponsive to the correct reset signal. If all other tests yield valid results, suspect the microprocessor. These three signals, then, are essential for every microprocessor: the power supply, the clock, and the reset. If any of these is missing or inadequate, the microprocessor will fail to operate normally. While these signals are absolutely critical to the operation of the microprocessor, they don't actually connect to front panels or control servos within the product. Instead, all of the action takes place with the input and output port lines.
The microprocessor used in a consumer product has two major roles: servicing the front panel customer controls and supervising the pickup, servo, motor, and signal processing circuitry. The customer controls in this CD player are very typical of those found in consumer products. Push-button switches and a multi-digit display are both located on the front panel of the player. The push-button switches are connected in a multiplexed arrangement through 3 output port lines and 6 input port lines. The push buttons are normally open switches which are connected across the intersection of an output line and an input line. In the multiplex circuit, one of the output lines is made briefly active while the other output lines are held inactive. The input lines are then read by the microprocessor. If a push button located on the active line is being pressed, the active output level will be read on the associated input line by the microprocessor. Each output line is made active in turn with a brief pulse. As each output line is pulsed, all input lines are read. Because each push-button switch is located at the unique intersection of an output line and an input line, the program guides the microprocessor to determine which push button is being pressed and what action should be taken. The keyboard and display output port lines are sometimes referred to as scan lines, since they're regularly pulsed or scanned in turn. When checking non-responsive front panel symptoms, the scan pattern on the output lines can be observed with the oscilloscope. The scan frequency is generally less than 300 Hertz. The outputs should stair-step their active states as shown here. The input line should also be observed for activity. When no push button is being pressed, the input line should remain inactive. When a button is pressed, the scan pulse should be present on the input line. By observing the output scan pulses and the input scan lines, it's easy to identify defective switches, resistors, and connecting cables. The front panel display is also multiplexed in an arrangement that is similar to that of the push buttons. The display consists of several digits which have their like segments connected together and fed from the A through O segment output lines on the microprocessor in this CD player. When the microprocessor outputs this segment pattern needed to display a character, all digits receive the pattern. The grids of the digits are driven by the 1G through 8G output lines on the microprocessor IC. Notice that in this player, 3 of the grid output lines were also used to scan the keyboard. That is very efficient use of the output port lines. The display's message is created when the microprocessor outputs the segment pattern for the first character to be displayed on the segment output lines. The microprocessor then outputs highs on all grids except that of the first digit, which is supplied a low. This low turns the first digit on and the character is visible. So while all digits get the segment pattern, only the correct digit is illuminated by energizing its grid. The microprocessor leaves the character on the first digit for a short time, then turns the digit off. It then outputs the next segment pattern and lights the next digit. Each digit is lit in turn. A front panel display and the microprocessor's associated output lines can be easily tested using the oscilloscope. All of the segment output lines should normally be pulsing in a seemingly random pattern. The grid scan line should have the same stepped output that was observed on the front panel push-button scan lines.
Display problems can originate in either the microprocessor or in the display itself. The digit scan pattern should be observed. If one line appears to be stuck, disconnect its pin from the microprocessor and observe its voltage. If it remains stuck, the problem is most likely within the microprocessor. If the scan pattern appears on the lifted pin, the problem is most likely in the display unit or the connecting cable. Any stuck segment line can likewise be tested. This microprocessor front panel interface is very typical of that encountered in a wide variety of consumer products. One other front panel interface technique often encountered in consumer products is seen in this typical VCR schematic.
Here the keyboard scan pulses, the display character segment codes, and the digit scan pulses are generated by a separate chip, IC 701, the Digitron drive. The Digitron drive IC is a custom chip that handles the push buttons and the display for the microprocessor, generating all of the necessary timing signals. This relieves the microprocessor of this relatively simple but time-consuming task. The microprocessor simply sends the information to be displayed to the Digitron drive and receives the push-button code from the push buttons. The scan pulses and segment activity should be seen on the Digitron drive lines.
The second function of the microprocessor in a consumer product is to control the servos, motors, and signal processing circuitry. It controls and coordinates the functions of these sections using two techniques. First, the microprocessor monitors some conditions in the product directly through simple on-off type switches and sensor inputs. This is commonly seen in a typical VCR.
The microprocessor's program will not let it perform any tape movement function until it senses that a video cassette has been loaded into position. It senses this condition through a simple mechanical switch, which is operated by the cassette. Because the cassette is either in position or it's not in position, the switch output is simple binary. It is low when the cassette is in position and high when it's not. The switch can directly drive an input port line on the microprocessor. The switch input can easily be checked with the logic probe or oscilloscope. Simply monitor the CST in line on the microprocessor as a tape is inserted and removed. The logic level on the line should toggle. If the level does not change, the switch should be tested, and if found functional, the line on the microprocessor forced. While this switch is simple, it plays a key role in the normal functioning of the microprocessor. There are typically several switch or sensor inputs in a product that monitor go, no-go conditions and are directly connected to the microprocessor's input port lines. When considering the trouble symptoms of a product, do not overlook these simple input devices and the easy tests for their proper operation. In most products, this kind of single-bit go, no-go status information is also provided to the microprocessor by other ICs in the system. These inputs can also be crucial to normal operation of the system. In this CD player, the focus OK signal is developed by the laser control IC1. This signal is high when the laser beam is in focus on the surface of the disc. It's low when the beam is not in focus on the disc. Focus OK is generated in IC1 and supplied to the microprocessor, which uses it to determine whether to leave the laser beam on, to resume a focus search, or to shut down the player. Here again we see a simple single-bit signal controlling operation of the unit through an input line on the microprocessor. And once again, the test is to simply monitor the FOK line with a disc in the player while the unit is being turned on or placed in the play mode.
Just as single-bit inputs provide much useful information to the microprocessor can perform much of its control function through single-bit outputs.
In the VCR, such functions as on-off control of the loading motor, the cylinder motor, and the capstan motor are easily performed through output lines. Proper operation of these output lines can be determined by simply monitoring them with the logic probe or oscilloscope during operation. When observing these lines, be sure to put the unit in the operating mode that will activate the line under test. If an output line is stuck high or low, lift it from the microprocessor pin and monitor that pin. If the output signal on the pin changes, the problem is likely to be in the motor interface circuit, not the microprocessor. If the lifted line does not change, suspect the microprocessor.
It is important to remember that the microprocessor will only change an output when all necessary input conditions have been met. Before changing a seemingly unresponsive microprocessor, carefully identify and test all related inputs. Many functional microprocessors are replaced when the problem is really a simple input device or a supporting chip.
When troubleshooting problems related to inoperative control functions, one other component should be carefully tested. In this VCR, the microprocessor outputs a signal to turn the loading motor on or off. The microprocessor itself does not have the power output needed to directly drive the motor, so the microprocessor's output signal is fed to the loading motor drive IC, which actually controls the motor. If the motor is unresponsive, this IC must be checked for proper operation. Monitor its input and output lines. If the input changes but its output does not, lift the output line and observe the signal again. If the signal is stuck, the drive IC is suspect. If the output signal changes, the motor may be defective.
The second monitor and control technique used by the microprocessor in many consumer products involves not single-bit control, but multiple-bit control through communication with other controller ICs in the product. These controller ICs might be other microprocessors, or they might be special purpose chips that are not sophisticated enough to be called microprocessors. Regardless of what they are called, the purpose of these chips is to control a section of the product under the overall direction of the main system controller. These chips relieve the system controller from time-consuming tasks. In other words, the application requires more sophistication and speed than a single microprocessor possesses.
The information that is transferred between the microprocessor and the other controller ICs is often in the form of control and command sequences. These sequences are patterns of highs and lows that are decoded to represent control instructions or system status information. There are two kinds of microprocessor to microprocessor communications commonly used in today's consumer product. The first involves serial communications over a single data line. Let's look again at the Digitron drive IC in the VCR. The system control microprocessor sends multiple bit display character codes to the Digitron drive IC over the data inline. Data can be observed here as a random looking pattern on the data line. Synchronization of the data transfer is provided by two additional signals. The clock line is supplied by the system control microprocessor to ensure proper timing of the data transfers. This line may either have a fairly stable signal all of the time or be inactive except when data is being transferred. The other data transfer control line is the strobe, also called the LS or latch strobe on the Digitron drive. The strobe signal is produced by the system control microprocessor and indicates when the Digitron drive should consider the bits sent to be a command word. This line should pulse as data is sent.
When observing serial data communications lines, it is important to be sure that data is being sent. That is, the product may have to be placed in the play mode to observe the transfer of data. Another caution about spotting the source of communications problems. Before an unresponsive chip is changed, observe the data, clock, and strobe lines on each chip. A break in the circuit board foil or a cold solder joint can disrupt communications.
Some system controller microprocessors employ a separate data line for each chip communicated with, as seen in the VCR. Since each device only requires 3 output lines, this is a popular technique. Other system controllers, like the microprocessor and this CD player, use a single data line for all chips. All of the data output by the microprocessor is supplied to all of the chips. The second basic type of microprocessor communication involves the use of more than one data line and the transfer of more than a single bit of information at a time. This technique is called parallel data transfer. Parallel transfer using several data lines is faster than using just a single line. Parallel transfer is often used between the microprocessor and the memory chips. The RAM in all CD players is fed data over 8 data lines. When parallel data transfer is used, all of the data lines should pulse. Any line that is permanently stuck high or low probably indicates a problem. Keep in mind that a stuck line can be created either by the sender or the receiver or the physical data path. So be sure to check all 3 before changing an expensive IC.
Well, those are the fundamentals of microprocessors in consumer products. When troubleshooting a microprocessor circuit, check the essential signals first. Then, verify the necessary inputs. Finally, observe the outputs. Use these techniques when you are tempted to replace the microprocessor to confirm whether it is defective. These techniques prevent changing unneeded parts, eliminate wasted time, and maximize your servicing profits.
We hope you found the information in this tape beneficial. A reference booklet has been included to help you review the information contained in the video. addition to this videotape, the Electronic Industries Association has a wealth of other information available for the professional consumer electronic technician and vocational technical educator. For further information, write EIA CEG, 2001 Pennsylvania Avenue Northwest, Washington, D.C. 20006.